Hi there, welcome to this AS Physics tutorial on vectors and scalars. In this tutorial, we want to look at all the theory as well as all the standard techniques that you need to know for this topic. The questions that we'll discuss in this tutorial are based on 20 past exams. So in question 1, we have to explain the difference between a vector and a scalar. So a vector is a physical quantity that has both magnitude, so both magnitude or size, so we're going to use the word magnitude or size, and direction. Then a scalar is a physical quantity that has magnitude or size only. So a physical quantity that has magnitude or size only, so no direction. Then in question 2 it says, next to each quantity below, write either the letter V for vector or S for scalar. Now, speed is a scalar, it has magnitude only. Velocity is a vector, so V, it has both magnitude and direction. Distance is a scalar, displacement is a vector, mass is a scalar, time is a scalar, acceleration is a vector, it's got both magnitude and direction. Momentum is a vector, force is a vector. Then pressure is a scalar, it doesn't have direction. Temperature is a scalar. Weight is the same as force, so it's a vector. Energy is a scalar. Work is the same as energy, so it's a scalar. And power is also a scalar. Then in question 3 it says, explain what is meant by the term resultant. So the resultant of two or more vectors is the net effect of the vectors. So the net effect of the vectors. Alternatively, we can also say that the resultant of two or more vectors is the single vector. So the single vector that can replace the vectors. In question 4, we have to find the resultant of the forces acting on each of these objects. We know vectors have direction, so conventionally we can choose to the right as positive and to the left as negative, up as positive and down as negative. Then in terms of notation that we can use for the resultant, we can either use R for resultant. If we're dealing with force vectors, we can also use F net or F res for the resultant. So let's look at A here. So the resultant force or the net force will be, we have a 10 Newton force to the right and also an 8 Newton force to the right. So both of these are to the right and therefore are positive. So it's going to be 10.0 plus 8.0, and this is 18 newtons. So note that both the 10 and the 8 here are positive since they act to the right. Our answer comes out to be positive, so we know the net or resultant force is to the right. So what does this answer mean? It means that if we replace these two vectors, these two forces, with a single force of 18 newtons, it will have the same effect as these two forces. In B, we have a 10 Newton force to the right and an 8 Newton force to the left. So the net or resultant force will be positive 10, which is to the right, plus this 8 newtons is to the left, so it's plus negative 8. And here the resultant will be 2.0 newtons. Once again, the answer comes out as positive, so we know this is to the right. Or we can even say east. Instead of to the right, we can say east as well. Then in C, we have a 10 Newton force up and an 8 Newton force down. Up is positive, so we can use positive 10. Down is negative, so it's plus negative 8. And our answer comes out to be positive 2.0 newtons. Once again, the positive here tells us that the net or resultant force is up, since we chose up as positive. Then in D, we have an 8 Newton force to the right and an 8 Newton force to the left. So this 8 Newton force we can make positive. This force is to the left, so it's negative. So 8 newtons plus negative 8 newtons. And of course here the answer is 0. So the net force or resultant force here will be 0. In question 5 it says, in the boxes provided, draw a rough sketch to show how you would find the resultant of each of the sets of vectors below. Label the resultant R. Let's look at A. So here we have two vectors that are neither in the opposite direction nor in the same direction. In this case, we can always use the triangle method to find the resultant with. So the triangle method. And how this works is we draw the two vectors head to tail, starting with any one of the two. So we can start with Q. So there's Q. And then we draw P so that it's head to tail with Q. So we have the first vector Q, and then the second vector P is at the head of Q. Then the resultant will be the vector drawn from the tail of the first one. So from the tail of Q to the head of the second one. So the head of P. So this will be our resultant R. Let's look at B. So here we have three vectors. Now, when we want to find the resultant of three or more vectors, we can always use the polygon method. So the polygon method. And it works in the same way as the triangle method. So we draw all these vectors head to tail, starting with any one of them. So let's start with Z. And the next one we can draw is Y. We draw them head to tail, and then of course X. Then once again, the resultant will be from the tail of the first one to the head of the last one. So this is our resultant R. Then in question 6 it says, in which diagram below is Z the resultant of X and Y? Circle the correct letter A, B, C or D. The first thing to note is, if Z is the resultant of X and Y, then X and Y must be drawn head to tail. In A, X and Y are not head to tail, so we can exclude A. In B, X and Y are also not drawn to head to tail, so we can exclude B as well. In both C and D, X and Y are drawn head to tail. However, for Z to be the resultant of the two, Z must be drawn from the tail of the first one to the head of the second one. And this, of course, is D. We can see here X and Y are drawn head to tail. And Z is from the tail of the first one, from the tail of the vector Y, to the head of the second vector, which is X. Let's look at question 7. It says here, draw a rough sketch to show how you would find the vector C, where C equals A minus B. The first thing we're going to do here is to rewrite this equation. So I'm going to write it as C equals A plus negative B. So from this we can see that the vector C is a sum of the vectors A and negative B. In other words, C is the resultant of A and negative B. What does the vector negative B look like? It has the same magnitude as the vector B, but in the opposite direction. So in order to find C, the resultant of A and negative B, we need to draw A and negative B head to tail. So let's start with negative B. And at the head of negative B, we need to draw A. So that's A. So these are head to tail. Then the resultant will be from the tail of the first vector. In other words, from the tail of negative B to the head of A. So this will be the resultant, C. In question 8a, we have to define displacement. So displacement is simply distance in a specified direction. So we know that distance is a scalar, whereas displacement is a vector. Another way to look at displacement is as follows. So let's say you walk along a certain path from point A. So from a point A to another point B. So let's say this is your path that you travel to B. What will be the displacement? The displacement will be the shortest distance from start. So from start to finish. So your displacement will be given by this vector or this distance. Let's say you walk along a path from a point A. So from point A, once again along some path back to A. What will your displacement be in this case? Well, the shortest distance from start to finish is 0. So in this case, your displacement will be 0. Then in B, we have to explain the difference between speed and velocity. So speed is the rate at which distance changes. So if you asked for the definition of speed in the exam, you can just write that speed is distance over time. Then speed is a scalar. Then velocity is the rate at which displacement changes. Once again, in the exam, if you're asked to give the definition of velocity, you can simply say velocity is displacement over time. And velocity, of course, is a vector. Then in question 8c it says, a hiker walks 3.0 kilometers from point A to a point B due north. At point B, he changes direction and walks 4.0 kilometers due east. If the hike took 3.5 hours to complete, find, firstly, the distance traveled by the hiker. Now, we can start with a rough sketch. He walks from a point A. So, point A will be our starting point. He walks 3.0 kilometers due north. So, we can draw a displacement vector due north. So, we know this is going to be 3.0 kilometers. Then, this will be point B here. So at B, he changes direction and walks 4 kilometers due east. So 4 kilometers. We need to find the distance traveled by the hiker. So we simply add these values. So 3.0 plus 4.0 will be 7.0 kilometers. Then in the second question here, we need to find the resultant displacement. Now, we know that displacement is the shortest distance from start to finish, or the straight line distance. So this vector will represent the resultant displacement, and we can call it R. We can use Pythagoras inside this triangle to find R. We know this angle is 90 degrees. So then R will be the square root of 3.0 squared plus 4.0 squared. And this, of course, is 5.0. So the magnitude of the resultant displacement is 5.0 kilometers. We know that displacement is a vector, so we also have to give the direction. We can let this angle here be theta. And we can use basic trig here inside this triangle to find the value of theta width. So the tan of theta is going to be 4.0 over 3.0. And using a calculator, shift tan of 4 over 3 will give us 53.1. So 53.1 degrees. We used two significant figures in this calculation, so we can give our answer also to two significant figures. So just 53 degrees. However, we need to be more specific here. So it will be 53 degrees east of north. So east of north. Next, we need to find the average speed. Now, we know that speed is distance over time. We worked out the distance. It was 7.0 kilometers. So 7.0. And we were given the time as 3.5 hours. And of course, this comes to 2.0. So the average speed then is 2.0 kilometers per hour. Now we need to find the average velocity. And we know that velocity is displacement over time. We have the displacement. It was 5 kilometers, so 5.0 over the time, which was 3.5. And we can do this on a calculator. And we get 1.4. So 1.4 kilometers per hour. And we also have the direction, which was, remember, 53 degrees east of north. East of north. So it says here, an athlete runs one lap around the track from point A, so from a point A back to A. So it goes all the way around the track from A back to A. Give a qualitative description of the athlete's average velocity. So we can start by saying that velocity equals displacement over time. So the average velocity will be the displacement divided by the time. Now, if he runs from A back to A, the displacement is 0. Because remember, displacement is the shortest distance or straight line distance from start to finish. So the displacement is 0, and hence the average velocity is 0, because we would be dividing by 0 in this equation. So hence the average velocity is 0. Then in number 10 here, it says a particle moves around a circular track at a constant speed of 2 meters per second. Explain whether the velocity of the particle remains constant or not as the particle moves around the track. Now, we know that velocity is a vector. So it has size and direction. We know that the speed is constant as the particle moves around the track. But what about the velocity? Is the velocity constant? Well, the velocity changes direction as the particle moves around the track. So we're saying the direction of velocity changes. And the moment the direction of a vector changes, the vector itself will change. So we know velocity is a vector since the direction of the particle or the direction of motion changes, the particle's velocity will also change. In other words, the velocity is not constant. Then in question 11 it says, a swimmer is crossing a river by swimming due north at 2.5 meters per second. The current flows west at 5.0 meters per second. Determine the resultant velocity of the swimmer's motion. So he's swimming due north at 2.5. The current flows west, so this way, at 5.0 meters per second. And we need to find the resultant velocity. So we can draw a sketch. We want the resultant of these two vectors. So we can draw them head to tail. So 2.5 due north and 5.0 due west. Then the resultant velocity will be this vector. So from the tail of the first vector to the head of the second vector. So this will be the resultant velocity. We know that this angle here is 90 degrees. So we can find the resultant by using Pythagoras. And this gives us an answer of 5.6, correct to two significant figures. So 5.6 meters per second. We also have to give the direction. So we can let this angle be theta. So the tan of theta using basic trig will be 5 over 2.5. And we can do this on a calculator. Shift tan of 5 divided by 2.5 will give us an answer of 11.3 degrees. The significant figures that we used here is 2. We use 2 significant figures in this calculation. So we can give our answer also to 2 significant figures. So it's going to be 11 degrees west of north. So west of north. Then in question 12a, it says explain what is meant by a component of a vector. So a component of a vector in a given direction is the effect of the vector in that direction. So in B here, we have to find the magnitude of the horizontal and vertical components of the force F as shown in this figure. So we have a force F of 10 newtons, making an angle of 30 degrees with a horizontal plane. We can add the vertical plane. Now, to find the component of the force F in a vertical plane, we simply drop a perpendicular onto the vertical plane. And the vertical component will be given by this vector. So we can write the vertical component as FV or even as Fy. Then to find the horizontal component, we similarly drop a perpendicular onto the horizontal plane. And this will give us the horizontal component, FH, or we can even use Fx as a symbol. Now, to find these components, we can firstly draw them head to tail. So FH and FV. Then the force F will actually be the resultant of its components, so of these two components. Now we use basic trig, we know this angle is 90 degrees. So let's first find FV. So we know that FV over F is the sine of the angle 30. The sine of 30. And so we can find FV, making it the subject, is going to be F sine 30. And so 10 times the sine of 30. On a calculator, this comes to 5 newtons. To find the horizontal component, FH over F. So FH over F will give us the cos of 30. So FH here will be F cos 30. So 10 cos 30. So 10 times the cos of 30. And we get 8.66, which we can round to one significant figure, to 9 newtons. Then in C, we have to write down the magnitude of the horizontal and vertical components of the force F as shown in each figure. So let's look at one here. Firstly, the vertical component. So we have the vertical plane here. Now note that this vector makes an angle of 90 degrees with a vertical plane. And that means that the vertical component will be 0. So whenever a vector makes an angle of 90 degrees with a plane, the component in that particular plane will be 0. Then looking at the horizontal component, the force F is in the horizontal plane. So the horizontal component will be the force itself. So it's going to be 10 newtons. Here, the force F is in the vertical plane. So the vertical component will be 10 newtons. It also makes an angle of 90 degrees with a horizontal plane. So that means that the component of this force in the horizontal plane will be 0. Then in D, we have to draw the component of the vector F in the northeast plane. So let's draw the northeast plane. So this will be northeast. Remember, this is north and this is east. Now, to find the component of this force in this northeast plane, we simply drop a perpendicular from the head of the vector onto the northeast plane. Then the component in this plane will be given by this vector here. So from the tail of the vector F to this point. So this will be the component of F in the northeast plane. Then in question 13 it says, complete each of the following statements by filling in the missing words. In A, for an object to be in equilibrium, all the forces acting on it must be balanced. i.e., the resultant must be 0. Then in B, an object is in equilibrium if it's moving at constant velocity. Or the object is stationary. So we know an object is in equilibrium if it's not moving or if it's moving at constant velocity. Then C, if an object is in equilibrium under the influence of 3 or more forces, the forces can be represented by a closed vector diagram with vectors drawn head to tail. So head to tail. Let's look at number 14. So here it says, which of the diagrams below, A, B, or C, represent forces acting on an object in equilibrium? So we're looking for a closed vector diagram with all the vectors drawn head to tail. So all of these are closed vector diagrams. If you look at A here, these vectors are not all drawn head to tail. We've got this one going that way, this one this way. They are not head to tail. In B, all these vectors are drawn head to tail. And it's a closed vector diagram. So we know B will represent forces acting on an object in equilibrium. If you look at C here, this is also a closed vector diagram with all the vectors drawn head to tail. So we know that this is also an object in equilibrium. So the answer here will be B and C. So in this question it says a 49 Newton box is being pulled horizontally along a rough concrete floor at a constant speed. And this is by a 25 Newton force that's applied as shown in the diagram. Draw a free body diagram showing the forces that act on the box. Now, when we draw a free body diagram, we can always draw a particle to represent the object with. So we have the applied force F of 25 newtons. And this, of course, is at an angle of 30 degrees to the horizontal. Then we also have the weight of the box down, or the gravitational force acting on the box. We can use W for weight. And we know that the weight is 49 newtons. We're also told that it's a rough surface or floor. and that means we have friction. The frictional force will always oppose motion, so it's going to be to the left. So we can use small f for friction. Now, there's one more force acting on the box. There's an upward force, which is the force that the floor exerts onto the box. And this is called the normal reaction force. We can use R for it. So R will be the normal reaction force. Normal, of course, here means perpendicular. We know this is perpendicular, or this is 90 degrees. Then in B1, we have to find the magnitude of the horizontal component of the applied force. So we want FH. And we know FH is F cos theta. In this case, F is 25 and theta is 30 degrees. And this comes to 21.65. We used two significant figures in this calculation, so we can write this answer with two significant figures. So round it up to 22 newtons. Then we also want the vertical component of the applied force. And we know this is F sine theta. So 25 is the applied force, and the angle, of course, is 30. And on a calculator, this comes to 12.5 newtons. And written with two significant figures, we can write it as 13. Then in C1, we want the normal reaction force R. Now, what's important in this question is that we are told that the box is moving at a constant speed. And that tells us that the box is in equilibrium. So it means all the forces are balanced. All the forces acting on the box are balanced, and the resultant is 0. Now, in this case, we want the normal reaction force up. So the forces up must equal the forces down. So we have the normal reaction force up and the weight down. But there's also the vertical component of the applied force acting up. So R plus AV up must equal W down. R plus AV up equals W down. R will equal W minus AV. W is 49 newtons and AV is 12.5. Let's see what that comes to. $36.5. Once again, with two significant figures, it will be 37 newtons. Lastly here, we want the frictional force, small f. Once again, we can use the fact that the object is in equilibrium. So the forces acting in the horizontal plane must also be balanced. We have the frictional force to the left, but we also have the horizontal component of the applied force to the right. And these two must be equal. So small f must equal Fh. And we do have Fh, the horizontal component. It was 22 newtons. Let's look at question 16. it says an object of mass 9.5 kilograms is at rest on a rough surface inclined at 55 degrees. In A, we have to draw a free body diagram showing the forces that act on the box. So we can start by drawing the incline as a dotted line and the box as a particle. So the forces acting on this box will be the weight down, or the gravitational force, and this we can call W. Then we also have the normal reaction force of the surface on the box. So we can write R for normal reaction force. Of course, this force will be perpendicular to the surface. Then we also have a frictional force up the incline that keeps the box at rest. So we can call it small f. Then in B, we have to calculate the magnitude of the component of the weight parallel to the surface. Now, what's important to note is that the weight can be resolved into two components. A component perpendicular to the incline or the surface. This will be the one component. We can call it W perpendicular. We have a second component which is going to be parallel to the surface or incline. So this is the component of the weight parallel to the surface, and we can call it W parallel. Of course, this angle here will be 90 degrees. What's also important to note is that the angle between the weight and the component of the weight perpendicular to the surface, in other words, this angle here will be equal to the angle of incline, which is 55 degrees. Now we can find the component parallel to the surface, so W parallel. And we can use basic trig inside this triangle. So W parallel will be W times the sine of 55. Of course, W is equal to mg. The mass is 9.5. G is 9.81. And we can do this on a calculator. And we get an answer of 76.3. So 76.3 newtons. The least number of significant figures that we used in this calculation are 2. So we can give our answer to 2 significant figures. So 76 newtons. Then in B2, we have to find the component of the weight perpendicular to the surface. So let's do that. Once again, we can use basic trig inside this triangle here. So W perpendicular will be W, which is mg, times the cos of 55. So 9.5 for the mass, 9.81 for G. And doing this on a calculator, and we get an answer of 53.45. The least number of significant figures that we used in the calculation were 2, so we can round this to 2 significant figures. So 53 newtons. Then in C1, we have to write down the magnitude of the normal reaction force acting on the box. We know that the box is at rest. So that means that it's in equilibrium and all the forces acting on it are balanced. So, for example, the forces that are perpendicular to the plane or incline, in other words, R and W perpendicular would have to be equal. And the forces parallel to the plane or the surface, in other words, W parallel and F must be the same. So W parallel down the incline must equal F up the incline. So to write down the magnitude of the normal reaction force R, so we know the normal reaction force R will equal W perpendicular. And we do have W perpendicular. It was 53 newtons. Then the frictional force acting on the box, so small f, we know must be equal to W parallel. And of course we do have W parallel. It was 76 newtons. Then in question 17 it says, a ship is pulled at a constant speed by 2 small boats A and B, as shown in the diagram. The engine of the ship does not produce any force. The tension in each cable between A and B and the ship is 4,000 newtons. The cables are of equal length. And we have to calculate the magnitude of the resistive force acting on the ship. So we can start by resolving the tension in each cable into its components. So let's start with the tension in A. So we have the tension in A called TA, and we have the horizontal component TAH and the vertical component TAV. We can do the same for the tension in cable B. So we have the tension in B called TB and the horizontal component TBH as well as the vertical component TBV. Let's write down expressions for these components. So starting with cable A, so TAV, the vertical component will be TA, which is 4,000 sine 40 using basic trig. Then TAH, the horizontal component in A, will be the tension in A, which is 4,000 times the cos of 40. Then the tension or the component, the vertical component of the tension in B, in other words TBV, is TB, which is 4,000 sine 40. And then TBH, the horizontal component in cable or of cable B, or the tension in B, will be 4,000 cos 40. So we can see that the vertical components of the tension in A and in B, the vertical components are numerically the same, but we know they're in opposite directions. So the vertical components will cancel. Then the horizontal components are also numerically the same, and they act in the same direction. So to get the net horizontal component, we can add them or take one of them and multiply it by 2. So then the horizontal component, the net horizontal component, TH net, will be twice TBH, for example. And this, of course, is 8,000 cos 40. Now, what's important to note is that the ship is moving at a constant speed, and that tells us that it's in equilibrium. So that means that in the horizontal plane, the forces are balanced. So to the right here, we will have the net horizontal component, FH net. And to the left here, we will have the resistor force, which we can call R. And these two must be equal. So the system is in equilibrium, so we know that the resistor force must equal the net horizontal component. They act in opposite directions, but both are in the horizontal plane. And we know this is 8,000 cos 40. And we can do this on a calculator. And we get an answer of 6,128.35. Now, in our calculations, we use the one significant figure. So our answer will be given with one significant figure. So this rounds to 6,000 newtons. So in question 18, it says a sphere of weight 2.4 newtons is suspended by a wire from a fixed point P. So the point P is over here, the sphere and the wire. A horizontal string is used to hold the sphere in equilibrium. So this is the horizontal string with a wire at an angle of 53 degrees to the horizontal. Calculate the tension T in the wire. Now, since the system is in equilibrium, or the sphere is in equilibrium, we should be able to represent all these forces, all three forces over here, in a closed vector diagram with vectors head to tail, or drawn head to tail. We can start with any one of them. So let's start with a weight. Then we can draw the horizontal force F to the left. So these are all head to tail, since the system is in equilibrium, or the object is in equilibrium. So F, and as we said, we can draw a closed vector diagram, and in the tension T. So a closed vector diagram with vectors drawn head to tail. This, of course, is 90 degrees. Then T makes an angle of 53 degrees with the horizontal. So this angle here will be 53 degrees. We can use basic trick to find the tension now. We know that W over T. So W over T is a sine of 53. And we want T, so we want to make it the subject of the formula. We can multiply through by T, and we get W is T sine 30, or sine 53. And since we want T, we make it the subject, so T equals W over sine 53. We are given that W is 2.4. And of course, this we can do on a calculator. And we get an answer of 3.005. And of course, here we used two significant figures in this calculation. So we can give our answer as two significant figures or with two significant figures. So 3.0 newtons. Next, we want the force F exerted by the string on the sphere. So we want F here. In this case, we can use tan. So tan of 53, or we can write that W over F. So W over F is a tan of 53. We want to make F the subject, so we can multiply through by F to get rid of this fraction. And in making F the subject, it's going to be W over tan 53. And of course, W is 2.4. So 2.4 divided by tan 53. And we get an answer of 1.81. But once again, we use two significant figures in this calculation. So our answer will be with two significant figures, so 1.8 newtons.